For image synthesis, achieving fidelity to a reference image while adhering to conditional prompts has been an open area of research. In this episode, we will be talking with Kshitij about his approach to this area of image synthesis. Welcome to the podcast.
Thanks, Leo.
Great. So let's start out with a high-level view of the paper. What computer vision issue specifically were you trying to solve in this paper?
Sure, Luke. So the primary issue we are aiming to address in this paper is the trade-off space between fidelity reservation and the prompt adherence while doing the conditional image generation. So specifically, when generating images based on textual prompts, it is challenging to ensure the fidelity in the to the reference image. So you have some reference image, you have some condition, which could be a text prompt. And now it is challenging to ensure both of them simultaneously. So fidelity is retaining the visual features of the context of the reference image while introducing new elements or modification based on the context, the textual prompt. And adherence to the textual prompt is something like ensuring that the generated image faithfully reflects the details and the conditional conditions described in that text. So now if you see at the existing approaches, they often struggle to balance these aspects. So either they are focusing too much on the text prompt, so the text appears more into the image, which can lead to the loss of important details from the reference image on which you want to draw that uh, textual prompt or the condition. And so, otherwise, what happens is they prioritize the fidelity to the reference, which can compromise the incorporation of that conditional text-based prompt into that image. So this is the issue which we are trying to solve in this paper.
Very interesting. And can you explain at a high level how you went about solving this problem?
Sure. So we tackled this problem by introducing a novel latent space manipulation technique, and it utilizes these importance scores, which we derive from the attention gradients. So I will explain that in more depth later, but the thing is, like in diffusion model, we have this unit which have these cross attention layers, and we derive the importance scores from those attention gradients. How it works is we leverage the latent space and compute the importance scores for that latent space. We have these importance scores. We do the dynamic masking, and in the end, we do some latent space manipulation to achieve the fidelity. We do some post processing for the smoothness as well. And after, when we combine all these steps, we achieved a balanced approach that improves both the fidelity to the reference image as well as adherence to the text prompts. So this is addressing the core challenge in conditional image generation. And I would say, yeah, like at high level, this is something we did to solve this problem, but I will explain in more depth with the ongoing podcast.
Interesting. Sounds good. So let's go into some background about you. What university degree do you have or are you currently pursuing?
So I'm pursuing master's degree in computer science at Georgia Institute of Technology. By the way, this is my last semester and I'm graduating in few days. So I'm you can say like I am graduated by now. And
Congratulations.
thanks you.
Great. And was this paper a part of your research at university or was it for a job?
So this was a part of my research at the university. So in the spring semester, I took the course Advanced Computer Vision offered in Georgia Tech. It is taught by the professor James Hayes. He's a very renowned professor in the field of computer vision. And I did this paper as a part of my research project in this course. And I focused mainly on the diffusion models, but this course offers you the all holistic concepts in the field of computer vision, I would say. So they discuss various aspects, topics like NERV is there, the diffusion models are there, then the latest image, the CNNs, and all such sort of the state-of-the-art models in the field of image processing. everything is taught in this course. So yeah, and my research was focused on the diffusion models. So I did that as a part of my research in this course.
Interesting. And did you open source any of the code used in this paper?
Yes, yes. So the code used in this research is open source and can be accessed. I can share you the link. You can put into the description of your video as well. But it's available. If you see my GitHub username, it's Kshitij79. So there is a repository called CS7476 Improvements in Diffusion Model. So you can access that there as well. And yeah, I will encourage further research and collaboration in this area. I will be happy if somebody looks into my repository and try to use that for further research, or if they need any kind of guidance related to this paper. I will be definitely happy.
Great. And did you present this paper at a conference?
Not yet. So this paper has not been formally presented at conference yet. However, I am exploring opportunities to submit it for relevant computer vision or AI conferences to share the findings with the broader audience, but not yet. Not yet. It has been formally presented and at any conference yet.
That makes sense. All right, so let's go into some more background about the paper. So what exactly is a diffusion model?
Sure. So to explain diffusion model, we can say like diffusion models are a class of a generative models in machine learning, which are used to create data similar to the data on which they are trained. So in our case, the data is image, and it's again trying to create that certain image. And these models works by simulating the process of gradually adding noise to the data and then learning to reverse this process. So the key components are forward process, which is the diffusion process. Then there is reverse process, which is reverse diffusion process. So what happens in forward process is we try to add some Gaussian noise into the input data and gradually transform that into a pure noise. So you had some input, you added some Gaussian noise, you had some noise output, and the reverse process is uh, this is where the model learns to denoise the data. So you have this noise data, and now you want to denoise that. So transforming noise back into a sample from the target distribution, which is the image in our case. And also there is one sampling procedure in the diffusion model. So after training, the model generates new data by passing randomly sampled noise through the learned denoising process. So this is a basic definition, I would say, in layman terms, how you can describe the diffusion model. So it is a class of generative models in machine learning. Yeah.
I see. And why is it so difficult to preserve the fidelity of a reference image while adhering to conditional prompts?
Sure. So preserving fidelity to reference image while adhering to conditional prompt is challenging because there are some noise trade-off. So when we introduce excessive noise, as I explained earlier, we have this forward process in the diffusion model. And when we introduce this excessive noise, it erases the contextual details from the reference image. So you had some reference image initially, and now you are doing this forward process. So you are erasing all those contextual details, which you don't want to do because you want that in the final output. So this is one of the reason. Other reason could be the limited denoising time. So the reducing noise levels compromise the model's ability to faithfully adhere to textual prompts due to fewer denoising steps. So if we somehow reduce the denoising time, let's assume we don't put that much noise into that image. So this will resolve the contextual uh, loss of contextual information. So since there are lesser number of noising steps, so contextual information retains, but the drawback is now we don't have much time to draw that condition into that image. The denoising steps are limited now. So that's the other trade-off space. So you are again uh, this time you are preserving the fidelity, but not the condition you are following. You are not adhering to the condition that effectively. Also, there is another aspect, like this was the trade-off space. There is another thing which is the interference effect. So the text prompt and the reference image often compete for representation. causing objects overlaps or unintended modifications, I would say, in the generated image, which you don't want to do. So these are the three aspects, I would say, which makes it really difficult to preserve the fidelity in the reference image while adhering to the conditional prompt. So this creates some trade-off space which we need to fix that out to preserve, to ensure that both the conditions are satisfied nicely.
Okay. And how does the absolute gradient-based selective attention manipulation better help you to preserve the reference image while adhering to conditional prompts?
Sure. So I think this is something viewers want to see, like what specifically we are doing in the absolute gradient SEM technique. Uh, Again, this will be a short description, but with time, we will be discussing it in more depth. So, but let me give you a glimpse like how absolute gradient-based selective attention manipulation, which is the APS, grad SEM in short, works. So it improves fidelity preservation by analyzing importance scores. So importance scores are the scores which are generated from that cross attention map in the unit of the diffusion model. Um, I think to visualize it more correctly, we should see the architecture of the diffusion model. But let me give you a verbal explanation for that. So using gradients of the cross attention map to identify the significance of elements in the latent space related to the reference image and text prompt uh, gives you those importance scores. Then you mask the irrelevant elements. So we create masks during specific denoising step to preserve critical features of the reference image while allowing the integration of text prompted features. And finally, we handle the bidirectional influence. So by using absolute gradient values instead of, so there is one more catch, like this grade SEM is motivated from one another research paper from Tel Aviv University. And they utilize that grad SEM to identify which part of the text is important in the next token generation. For that, they utilize this grad SEM. But the thing was that they utilize this rectified linear unit, which is a ReLU, which is a very common uh, uh, activation unit used in the neural networks. But in our case, we made it absolute, since when we are generating some latent space vector, the element, it could be positively or negatively influenced. So we don't want to like we can't discard any something which have some negative influence because it is getting influenced by the conditional image generation. So what we ensured is like it considers both positive and negative contribution of attention from that cross attention layer and enables us a more comprehensive manipulation. So now, in short, what we are doing is we are taking the importance score from the cross attention layer. We are doing some manipulation into the latent space, and ultimately we are getting newer latent space which have preserved the conditional image generation while also increase the fidelity of that image by masking that conditional image generation part. So this is how it's working. So absolute gradient is improving fidelity utilizing all these methodologies.
I see. And so can you describe how this approach of gradient self-selective attention manipulation was implemented in the world of language models, and then what you had to do in order to adapt it for use in computer vision?
Got it. Got it. So I think I explained one of the parts in the previous question, which was that this GradSEM is implemented from, like was motivated from one of the papers from Tel Aviv University. Let me tell you the name. It's GradSEM, by the way. The paper name is GradSEM, explaining transformers via gradient self-attention maps. And the author is Oren Barkan. He's from the Open University in Israel. And they utilize this technique in the transformers to explain which part of the text is helping to generate the next token. So it gives us the importance score. Okay, this part is influencing somehow the next token generation. So it gives us the importance scores. But the thing is, they were using the rectified linear unit. So they uses ReLU to capture the most impactful contributions, but we adapted it for our case. We made it absolute gradient. And I think I explained that why we did that in the previous part, but it was just to ensure like the impact we are considering both positive and negative contribution of attentions. So in language models, I would say GradSam analyzes the gradients of attention maps to rank tokens based on their relevance to a target word or phrase. It uses ReLU, as I said, for adaptation to computer vision. We modified the gradient analysis to use absolute values, as pixel level attention can have both positive and negative effects. We applied GradSam to the latent vector in the denoising process, targeting specific time steps to manipulate cross attention selectively. So we are not doing it for all the time steps. We are choosing certain time steps. If I recall correctly, like for our case, for this paper, we identified the time step like 5th, 10th, and 17th, which were giving us a good results because it had significant time to recover uh, that overlapping the masking part which we are doing, because sometimes there could be some disruption when you put some part into that latent space. So you need some time just to make sure that the transition is smooth. So this is another aspect. Like we are not doing it for all time steps. We are targeting specific time steps to manipulate cross attention selectively. And we designed mask for spatial preservation, ensuring the integrity of visual features while integrating text prompted content. So these are the other things which we did apart from taking the motivation from GradSam, just to make sure that we are able to implement that it for our case, which is the computer vision problem. So GradSam was for the transformers. Now this is for the computer vision, but I think the methodology remains the same. It is just about picking up that attention map and applying, calculating all those absolute gradients carefully. So this is what we did for the adaptation for the computer vision part.
Great. And so how did the text-to-image diffusion models build upon the baseline of the classical denoising diffusion probabilistic models?
Sure. So text-to-image diffusion models extended DDPMs by introducing conditional guidance. So we incorporated cross-attention mechanisms to align image generation with textual prompts. We fine-grained the control, so added latent embeddings to condition the diffusion process on text inputs. Then, apart from that, I would say there was iterative optimization. So we refined the noise prediction model to achieve higher fidelity and alignment with complex text-image pairs. So I think there wasn't much of the extension from the DDPMs, but few of the things were these, like the conditional guidance, then the fine-grained control. There were few iterative optimizations. So it's basically the DDPM, I would say, apart from the implementation part. So yeah, this is it.
Makes sense. Next, can you compare classifier guidance with classifier-free guidance when controlling for the trade-off between sample quality and diversity?
Sure, sure. So I would say like classifier guidance is something which is not used by the recent state-of-the-art models, also not for the production. But in earlier days, we used to have this classifier guidance, which uses a pre-trained classifier to steer the denoising process. So this is computationally more heavy, I would say, classifier guidance. You have two models, one which is just taking the input image and is able to give you the regenerate that image, and other is you have some image generation model which is fine tuned over some condition could be textual, anything, but uh, you can take a lots of example instances for that, like for you have some condition to generate only the dogs, So the model is trained to generate the dogs only. So now, since we are doing the conditional image generation, we have two tasks. One is the condition, one is the naive image generation. In classifier guidance, we give weightage to both of the image generated. So both the generated images have certain weightage, and based on that, we update the model's weight just to make sure like it is able to do both the stuff, the conditional generation as well as the image generation. So for the image generation, we have the reference image. We are able to generate the reference image. For the condition, we are have the condition, and we are able to generate the conditional image. We are intertwining both of them, and ultimately, we are getting the final output, which have both the characteristics. And now, in classifier guidance, if you want to increase the weightage of the dog creation, so you can ensure that by increasing the weightage for that uh, the conditional model. So if you increase that weightage, you will start getting more emphasis on that condition generation. Or otherwise, there will be more diversity in the background. So different sort of backgrounds will be generated. But what we did in classifier free guidance is you utilize the same model, and we are training it on both the tasks. So one when we give the condition and when we don't give the condition. And so now this is again a trade-off space. Like either you want the quality of the image, the condition to be high, or you want the diversified image. So we are not doing, we are specifically following the classifier free guidance in our paper. But this is the basic difference, like how we can compare the classifier guidance with classifier free guidance when we are controlling this trade-off space between the quality and the diversity. And as I said, for our paper, our focus will be more into the classifier free guidance, and there could be some confusion, like absolute gradient sum technique, which we saw earlier, where we are manipulating, is also trying to uh, manipulate images in that context, but not completely. So there is one difference which I find really significant here is for the classifier free guidance. We are just ensuring that either the condition is followed really well or the image generation, the background is followed really well, but it's not ensuring that fidelity of the initial image is ensured. But we, in our technique, we are also ensuring that. So that's how it differs from these classifier guidance concept. So this is another enhancement, I would say, when it comes to follow some condition. So classifier guidance help you to follow the conditions with improved diversity, but our technique makes it more, it's a further enhancement in terms of the fidelity from the base image. So now you are drawing the condition as well, but also following the fidelity really well. So this is it.
Interesting. Cool. Next, let's go into more detail about your methodology. Can you describe the first step of encoding the input images?
Sure. So I think this is the same as any other encoder, like how this is the typically how the encoding works for the input images, but in just for the clarification and uh, following our paper. So in our approach, the input image is first passed through some encoder to transform it into a latent space representation. And the encoder is a part of an autoencoder architecture. So we had some autoencoder, which had encoder, then the latent space, then the decoder part. And the encoder, its role is to reduce the spatial complexity of the image. So this is how the encoders work, but their role is to reduce the spatial complexity of the images while also preserving essential features. This latent representation allows for more efficient manipulation and generation within the lower dimensional space. So image is really high dimensional. Now you get that image into some lower dimensional latent space, and further you can do some of the experiments around that. So this is the process which we followed.
Great. Next, can you describe the second step of adding noise to the images?
Sure. So this is again the fundamental part of the diffusion process, and The diffusion process starts by gradually adding Gaussian noise to the latent vector over several time steps and transform it into a noisy representation. And this is referred to as the forward diffusion process. So the process is noise is added iteratively to the latent vector, and uh, mathematically it's some Gaussian equation, like some Gaussian noise is getting added into that latent vector. So, and with the time, as the time increases, the error also increases progressively, and eventually we are kind of approximating pure Gaussian noise at the final time step. It is a mathematical concept; it's a proven one, but ultimately, whatever we get is a complete pure Gaussian noise. And this step helps to model to learn how to reverse the noise during the denoising process, enabling it to generate realistic samples from that random noise. So we are having some random noise and still we are able to generate some image. So that's the process we want our model to learn, which is the unit part of that diffusion model.
Interesting. Now, can you describe the denoising step, which leverages the UNet architecture to predict noise at each timestamp?
Sure. So the denoising step involves reversing the forward process using a unit-based architecture. Uh, I think I have used the unit word multiple times during our discussion, but this is where we want to use our units in methodology. So the unit predicts the noise. So its job is to predict the noise epsilon at each time step t. During the so time steps works like this. Like if we did the 50 followed the 50 time steps for noising, then during the reversing, we will be going back from 50 to the first time step. This is what we desire to do. We don't do that eventually, since due to the randomness of the machine learning models as well as the condition which we are providing, which differs the output. But during the training phase, that's what we train on. Like if the reference image is this and we want the output this, then all those time steps are utilized to ensure that the generated latent space is very close to that initial at that time step noise latent space. So yeah, but let's focus on the unit. So the unit predicts a noise. Uh, so let's say epsilon at each time step, and gradually removes it from the noised representation of the latent space to the unnoised, denoised. And the process is simple. For each time step, there is again heavy mathematics involved out there. I think the best paper to know all that is the DDPM paper. We can put that link into the description of this discussion. But yeah, the predicted noise is kept on subtracted from that latent space. And ultimately, the cross-attention mechanism in the unit aligns the latent features with the conditional input. So by we apply this process iteratively, the diffusion model progressively denoise the latent vector, and eventually we produce the denoised latent vector. So, yeah.
Great. And finally, for the last step, can you explain the mask creation for the latent space manipulation?
Sure. So this is something the key part of this paper. The algorithm which you will see in this paper explains how we are creating this mask. And these mask is something based on the importance scores. So, but still, let me go through from the basic fundamentals. Like the mask creation process, which we are following, is utilizing the importance scores, which we derive from the gradients of the cross-attention maps in the unit. And these masks selectively preserve key elements, example subjects, from the latent vector while allowing other agents to be modified based on the reference or conditional input. So the process is simple. We first compute the gradients. For our experiments, we have only utilized the last cross-attention layer for this paper. This is computationally really heavy. You have to have your complete graph of the neural network. Then you have to do all that back propagation and also, which is really computationally heavy. If you don't have the resources, you won't be able to do that. And for even for the last layer, I would say it takes a significant amount of GPU. So, but yeah, so let's focus on the last layer gradients, and based on that, let me explain like how I am doing this mask creation. So the process is simple. First, compute the gradients. So for the cross attention layer, ideally you should be doing it for each cross attention layer. In my case, I did it for the one. Compute the Jacobian of gradients of the noisy latent vector with respect to the attention weights. Now calculate the importance score. So importance score follows the Gretzheim concepts. So we will be taking the absolute Gretzheim, and we will derive the importance scores for each spatial location. Spatial location is the pixel in that latent vector. We will do that on the gradients and the attention weight. And this is again a mathematical concept. Like we have done some utilize this absolute gradient SAM techniques to create all these importance scores. We have did some Hadamard product, which is simple product. I would say it's a dot product, but yeah. And utilizing that, we generated these importance scores. Then we created this binary mask. So generating a binary mask for each subject is by thresholding the importance score. We did some thresholding. Obviously, like we need to determine some threshold, which could be done empirically and experimentally determined. Like this could be a threshold, which we will say like is not important that much, or is it important? Should we conserve that pixel, the spatial information, or shouldn't we should not do that? So that's determined by that threshold. And ultimately, we combine the mask from every cross-attention layer. For in our case, there was one layer, so we don't have to take the union. But you have to take the union for all subjects. You don't have to take for the cross-attention, which is deemed like this is what we expect for. If we have multiple cross-attention layer, we will be doing the uh, union for multiple cross-attention layers. But in our case, we had one cross-attention layer, but we had multiple subjects. So subject is the thing. There are two level of union which we are taking. So one is for the subject specific, other is for the cross-attention specific, layer specific. So for the we will be taking the union for all subject mask, and we will be taking the intersection for all layers, attention layers. Pardon, I think I did one mistake. So I told the union, it's the intersection for the layers. So for the cross attention layers, you will be taking the intersection of all mask which is generated for each cross attention map. For each subject, you have some attention map. You have some mask based on that created, and you will be taking the union for that. So that's the resulting mask which you will be creating, which identifies the regions to preserve or modify during the latent space manipulation. So this is how we create the mask.
Interesting. And how did you mitigate the issue of having abrupt transitions at the boundaries of the masks?
Sure. So to addressing the abrupt transitions at mask boundaries, we applied multiple like we did experiments with multiple techniques, but ultimately we applied this Gaussian blurring and morphological deletion, which are the famous image processing techniques, I would say. So Gaussian blurring is like smoothing abrupt transition by convolving the mask with a Gaussian kernel. You have some Gaussian kernel, and it have the parameters like the standard deviation and the mean, and you do some convolution. So it smoothes that out. It does some Gaussian blurring. Apart from that, I utilize the morphological dilation, and it expands the boundaries of the mask to ensure smoother transition and eliminate artifacts. So there are very abrupt, sharp uh, edges which you will get after creating this mask, but you don't want that. You want that smoother. So dilation also help in that context. So I think, yeah, these two things were used, the Gaussian blurring and the morphological dilation. And by combining these operations, we ensured that the mask have smooth transitions, reducing visual artifacts, which doesn't matter that much when the things are in latent space. But still, the ultimate result which we got after doing this promoted the seamless integration between preserved and modified region in the latent space, and even the generated images were really good. And we played around some of the fine-tuning parameters like sigma for Gaussian blurring, and also the structuring element for the dilation. And we optimize these results further to ensure that we don't have the abrupt transitions at the boundaries of these masks.
Interesting. And so now let's go into some experimental questions. For your experiments, what model did you use?
So I utilize the stable diffusion version 1. It's the version 1 have multiple variants, like they have played around with it. Some they have utilized the clip embeddings, for other they have utilized their models embeddings. So for specifically, I utilize a stable diffusion model version 1. It's I think got released in back in 2022, and it's around, if you ask me how much memory it takes, it's around 4.7 GB if you download it online. It's available on the Hugging Face. One thing I want to highlight for the viewers, like if you are following my paper, the link, the citation in my paper is bit outdated, and the link which I have used there is utilizes this runaway ML. But you shouldn't be using that. I would recommend, the link has been changed. You can see in my repository, the GitHub repository, and there is a slight change. But yeah, like that link won't be working, but it's available on the Hugging Face. And if you see my GitHub repository, you will still be able to use all those scripts to download this model state. But if you try to open that link in the Hugging Face, that won't be working. So again, we can provide that in the description if that's visible uh, for this discussion. So yeah, just mind that link is not working right now. So
Absolutely.
yeah, thanks, Luke. So this model was actually the version 1, fifth model uses the clip model for generating text embeddings to align the input textual descriptions with the generated image. Additionally, we fine-tuned this stable diffusion model and integrated the absolute RedSim technique for improved fidelity and alignment. So this is the model, stable diffusion version 1, fifth model we utilize for this task. And one more thing I want to give credits to, just a minute. I forgot the name, Umar Jamil. So I got motivated from his repository. So he have done the same thing in one of his GitHub implementations, and I followed him. He have mentioned all these aspects, how he utilized, how he did the setup for this diffusion model. And in the initial stage, I followed him. After that, lots of changes were done to do all these experiments, as well as all these absolute gradients and implementation. But the base code I have taken from the Umar Jamil repository. Uh, so yeah, shout out to him as well. So this is it. This is the model which we used for our experiments.
Great. And what metrics did you use to assess the quality of the generated images?
Sure. So we relied on two key metrics. There could be other metrics as well, but I think these were the most priority one and defined our trade-off space really well. And one was the FID, which is the fresh ray inception distance score. So it measures the similarity between the distribution of real and generated images in feature space. And other was the clip scores. So clip scores evaluate the alignment between the generated images and the corresponding textual prompts. So if you have the higher clip score, it suggests better adherence. It's a similar to the cosine or similarity scores. So more higher score you are getting, more closely aligned your context is with that image or whatever the modality you are using. Clip is specifically for the language image, so the text and the image. So higher clip score means high better adherence, and for FID it should be lower. So lower FID scores indicates better fidelity to real images. So these are the two metrics, FID and the clip scores, which I utilize for accessing the quality of these generated images.
All right. And what were the results of your experiments? How did your model compare with the SD tuned and the SD baseline on the metrics?
Sure. So let me give you a bit of context, like what is the SD. So SD is the model which don't have hyperparameters optimized. And hyperparameters are like the value of the CFG scale, the classifier free guidance scale. Then we have how much noising do we want into our image. So all these parameters were something which also there is there were other parameters as well, like how many images you want to generate, uh, what is the noising level, what are the parameters you want to set for that, and certain things. But for the ST part, we haven't optimized that, and that's why the results were not really good, I would say. For fine tune, we fine tuned that stable diffusion model, which is called SD tuned in our paper. So we identified the best hyperparameters, which will be giving us the best result when it comes to the FID and the clip scores. So that's the part covered in the SD tuned. And finally is our model. So when we compare our model with the SD tuned and the SD, which is the baseline, so we saw some uh, significant improvements, I would say, when it comes to the clip score. So clip scores are really high uh, than both of the models, SD tuned as well as SD. So our model performs really well in that aspect. The score were around 0.2798. In paper, I have like scaled it to the 100. So if you say there, it is mentioned 27.98 as a mean and the median is 28.24. But that's a scaled score. In the reality, it was like 0.2798, which is the actual cosine value between 0 and 1. And so clip scores were really good. And when you compare the FID scores, FID scores were still good. But if you see, compare it with the SD tune, it's slightly low, uh, which which is good thing. So the thing is, for the FID scores, when you want FID scores for some images, you want it to be lower than the images which are getting generated. So the thing is, pardon, but the thing is, like, when you want lower FID scores for your image, that ensures like how much image is preserving the fidelity with the original one, and which was really good. It was 6.89 for our case, which was the mean, and the median was 5.32. If you see it for the SD tune, it was around 8.21 and 6.97. I'm just seeing the result in my paper as well. Yeah, yeah. So pardon, yeah. So these were the results. For the baseline, the results were really not good. For the FID scores, the mean was around 15, the median was around 14. And so our model did well when it comes to the FID scores. It achieved the lowest FID scores, indicating a better fidelity and closer resemblance to the real images. For the clip scores, while primarily focused on fidelity, our model outperformed the competitively in aligning with textual prompts. So both are good. The FID scores are good and clip scores are good, which we wanted to show through our implementation, that using such technique can significantly improve both these scores.
Very interesting. So let's move into some finishing questions. Where might some future work be able to build upon your work that was done here?
Sure, sure. So for the future works, I think there are lots of aspects which we can cover. Uh, there are certain clear uh, so one thing is that explainability and interpretability for these models is something which is not that good, and enhancing the explainability of latent space manipulation makes the model decision more transparent for practical use. So assume some people who are trying to create the systems for these image generation, they don't know how this black box is working. But if you can see how the latent space works, how you can manipulate that, so that really leads up to the explainability. So some work around that could be done, and more analysis, like currently for this paper, I only utilize these gradients. But which cross attention layer is the best one, which is impacting that image generation, you can identify that. Lots of experiments could be done for that. Also, a specific model might have more weightage into some other sort of features generation, which will be different for other models. So you can explore that part as well. So like this kind of study, so why this paper is so unique is because it don't only relies uh, on any other network. It only utilizing its own properties to do all this enhancement, tweaking into the agent space, which is missing in other papers. I would say my paper compares best with the control net. Control net is another paper which is widely used in today's scenario, and this does the same. It takes one image, then it takes the condition, the kind of condition which you want to insert into that image, and it intertwines both of them to finally give us the output. But it differs in some aspect, like you need to have again a trainable copy of the same model which you had earlier. So you are now increasing the model weight by the twice. So there are two networks competing together. Not competing, I would say working together, but you are making the architecture really bulky. And in our case, we are not making it bulky. We are just utilizing the explainability and the interpretability part to make sure that the kind of images which we are generating are really good. So this is the one part, explainability and interpretability. Other thing I would say is improving the fidelity preservation. So we can see from the results, it's improving the fidelity. It's also preserving the context adherence. So this is something which can be really utilized by all the developers out there who are developing the systems for image generation. Uh, Other aspect which could be covered is like generalization across datasets. Currently, for my research, I only utilize the place 365 data, but it could be generalized across multiple datasets. Also, the real-time applications. So, adapting the model for real-time or interactive use cases, such as creative tools for artists or content creators, is something which could be this research could be utilized for developing such applications as well. Adobe is the pioneer in this field. I think they have multiple such models out there in Photoshop, Adobe Photoshop. But yeah, this is something, but they utilize some different techniques than this. So this is a research which where you can only utilize a machine learning model to generate all such sort of images, and it will be really helpful for the creative tools and for the artists who are generating the content. So I think this is something where this future work, like lots of future work could be built upon my work here.
I see. Perfect. And finally, is there anything else that you'd like to shout out for resources or your work?
Uh, I could shout out for the Georgia Tech. So Georgia Tech provides us the PACE clusters. So PACE clusters are the clusters where anybody who wants to do the research can take the resources and do all kind of research work. They have their dedicated space. All sort of GPUs are available there. We have V100. The latest one is, I think, H100 or RTX. So the Georgia Tech provides you the free access to every researcher of that. And for any kind of research, you can utilize their GPU, their computer resources, and you will be able to do your research. So a special shout out to Georgia Tech for that, for providing all such resources, which are not so easily accessible. Apart from that, I will shout out to the paper, this attend and excite. I think I didn't mention that before, but I got motivated from that paper. This paper is written by Hila Sheffer. I think she is in the Google doing some research. So yeah, thanks to that attend and excite paper. Other than this is to the Umar Jamil, whose base code I utilized to set up the diffusion model initially. So yeah, thanks for that as well. Then the Gradson paper from Tel Aviv University, which was again really helpful to identify how I can do all such manipulation. So I think this is it. And I believe this approach has tremendous potential for individuals and teams working on systems for image generation and photo editing. With the ever expanding arsenal of techniques to enhance conditional image generation, this methods adds another powerful tool to the mix. And by leveraging explainable latent space manipulation, it not only improves fidelity but also ensures better adherence to prompts, offering a significant boost in overall image quality. So admittedly, I would say this technique comes with computational challenges as the resource amount scales with the number of cross attention layers utilized. I explained that earlier as well, but like if more cross attention layer you want to use, more GPUs compute you would need. But however, for system optimized for generating high quality images, incorporating this enhancement can lead to remarkable improvements in both precision and contextual alignment. And I think the systems which generate all such image generation systems which are out there, they have all such compute available already, because in fact they are not even generating single image, but there are multiple images, multiple GPUs working out there in the system which are giving you that output. So that is something I would say, like the systems can be further optimized for generating high quality images by incorporating this enhancement of our paper. And in the end, this methodology demonstrates how combining innovative techniques like absolute gradients with state of the art model can push the boundaries of what's possible in image generation. It's an exciting step forward for the field and opens door for future research and application in the creative and technical domains. Like,
Amazing. Great. That's all my questions. Thank you so much for coming on the podcast.
thanks, Leo. I really enjoyed your questions, and yeah, I thoroughly enjoyed all your questions. I uh, really liked explaining my papers. I hope I was helpful for explaining all the aspects of these papers, and people will find it beneficial in their research. And I will really appreciate if they use my research work for future collaborations as well as for their future research.